Okay, we'll try that again. I will never get tired of having OBS update and reset my sources for my microphones. Not just one, both of them. It seems religiously every time this stupid program updates, it decides to reset the program. This is not the face I want to be making today. I have stuff I want to do. So, we got that fixed. Hello, everybody. I love trying to watch the closed captioner attempts to figure out what I'm trying to say when I kind of throw those punchy little quips at it, because it doesn't quite know what I'm trying to say. It's kind of fun to watch it attempt to decode the toaster. Alright, my chat window has run off without me. Let me see who is here. Oh, we had a Porsche lurking in the bushes. Hello. And I see a pine and a cozy. And I see the fact that I muted. Woo, Porsche with the 3-stream streak. Yeah! That's awesome. Much excellence. Cozy hears me. Oh, no. That's their first mistake. Toaster's talking. Yeah, something about Autobots. No, Autobots? Let's try it again. Autobots. You know, in the Decepticons. When the toaster starts laughing, that's usually a poor sign to things to come. But besides that point. Okay, so here's the plans for this evening. Or at least the attempt of a plan. Fingers crossed that I have everything plugged back in where it's supposed to go. Because the last time I had the Proot out on the bench, I had to take it partially apart to stick it back in a box. I think I have everything where it belongs. The discussion for tonight is going to talk about toaster. Indeed, much toast. Very wow. Welcome on in, Thunder. The discussion tonight is going to be about figuring out the battery for the Proot head. So I've got some toys on the bench for us to play with. We're going to read, well, the voltage is going to be 5 volts on everything. That's a spoiler. But we do need to figure out is how much amperage the different things draw. Figure out the calculations for the battery, of how much we need for the amount of time we want to put out. And then add in some, some buffer. Yeah, so what? What are we doing? I'm okay. I'm staying entertained. So yes, we are going to figure out the what. What? Indeed. So that's the plan. We're going to figure out how much battery we need, and then I might do a little back and forth here while we try to determine if that means that we may be able to work with an off-the-shelf battery and then be able to step the voltage up and down to hit 5, or if we will end up making one. I'm gonna be honest with you, I haven't made up my mind yet on what's going to happen on that. So we're gonna do a little research tonight. We're gonna see what kind of values we pull, and maybe find a direction for where we're gonna go with this. I have not touched anything with the Protogen build since the last time I talked about it live on stream. So if anybody is wondering, no, nothing has changed. The last time we left off, we got the faces working, we have the fan controller working, we have the menu integrated, the controller functioning. We are now to the point of figuring out how to power the project. And then as time progresses, my plan is to try to work on some, try to figuring out how to put together some like basic animations for the faces, while we work on actually building the head. So, I'm less concerned about, the rest of, I'm going to refer to it as making it pretty for what appears on the screens right now. I have enough of the code to figure out how to get just the basics together. And then I still plan on improving on that as we continue the build. But to be honest, I want to start working on putting the physical aspect of this together. I have enough of the hardware together that I'm convinced we can proceed forward with the next couple of steps, and then, you know, we'll work on making some additional expressions, maybe clean the looks up a little bit. But It's okay because we're gonna have to showcase the whole setup of where we're at right now tonight, so that I could cycle through some of the different things, and we'll put the whole system under load, get an idea of how much power it draws, and then we're gonna math. I have Excel open right now. We are going to math, but that's okay. This will be functional math. Anybody who's ever built anything electronics related knows that if it's not going to be plugged into the wall, you have to have an idea of how much action is going to happen, or it won't last, you know? So it won't meet expectations, I should say. He is an IT gamer. Hello. Put system under load. Kaboom. Yeah, we are attempting. Okay. I don't currently have eyebrows, but if I did, I'd like to keep them. So there's that. Okay, so first thing we're gonna do is I'm gonna pivot us over to the bench. I do not have the laptop out tonight, so I have Excel open on the primary rig. So we're just gonna do the math there, but we're just gonna cycle back and forth between the bench and the action I have over here. So first things first, we're gonna get up in here, and I'm going to attempt to show you guys stuff, and I'ma do stuff. So like last time, I have the variable power supply set to 5 volts and light on here, and it will tell us how many amps are appearing on the display. So that's just off camera, and the way that it sits, it's super awkward. Like I don't have a good way to showcase this once we've plugged stuff into it, but this is it right here. So we're set to 5 volts, and then the bottom number here is going to be the amperage that I'm reading off of the display, and then I'll type that into our formula as we're figuring things out. So it's the last time you're going to see that on camera, because it's awkward once I start plugging wires in. I'm going to demonstrate the 1, 2, 3. Please don't blow up. Yes, exactly. I came into this house with my eyebrows, and I would like to leave this house with my eyebrows. That's the idea. Okay, so since we're working with USB-C powered things, right? We got our USB-C cords, and our accessories work off of USB-C, right? I need to get an idea of how much power this is going to draw. And my plan for these, the one for the controller and the one that runs the display, is that we're going to leverage the USB-C connectors on here, which means that to get a good voltage reading, we need to get some readings. What we have here is 2 different volt and amp readers that are USB. Let me get the little protective cover off of there. So I've got a USB Type-C one, a USB Type-A one, and then as I flip this over, we've got the pass-through for just the USB Type-A and the USB Type-C. So what we're going to do is we're going to put the system under load with these connected between each individual wire to figure out how much power we're going to draw. Now looking at what I actually have here, we actually don't need this one. We need this one because everything here on the bench actually is USB-C. So we just have to do it one wire at a time. I'm less expecting for the controller that we're going to use to change the expressions to really draw too much power. But I am curious to see once we start, navigating the menus, if that creates any meaningful draw. I'm not expecting it to, but we're going to find out. So, with enough of the ramblings out of the way, first things first, we're going to do a power tap draw on the controller. So, I'm going to take our little buddy here and plug it in like so, and then we'll plug our power into there. We'll boot up the system, and then we'll start interacting with the controller and seeing if the values on this change at all. So it doesn't matter which order I boot these in, so I could boot this one first, and then it's just going to wait for input from me. Okay,
Okay, so I got that there. And then let me get some power to the displays and the microcontroller. And then we'll go from there. So slightly off camera, I've got the fan and the leads for both displays. Okay, so I got that. And then I've got my positive and negative for the displays. I'll hook those up. And then before I connect the negative to ground the system and fire up the displays, I'm going to connect the USB to the microcontroller first. I still have to figure out what's going on that causes grief, that prevents the second microcontroller from booting. Oh, that's funny, I don't have this grounded yet. How are you lit up right now? Oh, duh, never mind. It's getting its power from the USB. I'm like, wait a minute. That's not right. Okay, so I've got a fan. I have to be careful that I set this in a way that I don't short anything out here. That's the fun thing about having an awful lot of little wires just kind of all over the place. Okay, so I have a really wide angle shot here. And we have the... All right, cool. So we have the whole setup booted right now. So as a recap, for those of you who are maybe new, or just don't remember, because frankly, it's been several weeks since I've had an opportunity to work on this. We've got both sides of the face that's going to appear inside of the Protogen head that we're working on building. That gets power from the black and red wires here. It comes off the power supply. And then from there, we have our controller that we're going to use to interact with the menu I have over here. You can see that very, very briefly in the corner of my camera to interact with that menu. That menu is going to appear in two places. It's going to appear on the inside of the head, mounted to the back of one of these displays. I'm probably going to put it on the left-hand side, just so I can look up to my upper left to see where I am in the menu. And then I also am planning for the suitor, because this project is going to be made public when I'm done with it. What's going to happen is that I'm going to have a display that's going to be attached to the controller board that this is hooked up to, so that you can see on the inside what's displayed, but also a little display on the outside, so that if you hand your controller off to your friend or your handler, they can control your face, but you on the inside will know what expression you're making. That way, that can free up both of your hands if you have someone who's playing buddy to help you change your expressions. So that's the thought process if you haven't seen this before. So we have our current face and then the fan speed for the fan controller that's just out of frame. you can't quite see it. Can I slide that? Nah, I'm not gonna bother. You'll probably hear the fan. So right now, I'm gonna record a couple of things here. So I'm gonna pivot us back over to the computer because I have a couple of values I want to write down. Okay, so first things first, we're going to put in here the voltage. Everything is going to have a voltage of 5 for this current instance of the project. We'll have the item, the voltage, and then the max milliamp hour, lowercase h. Milliamp. MAH, what is it? Is it capital A in the middle? That's why I'm screwing up here. And capital A, H for milliamp. There we go. And then we have to figure out our watts. And then we'll work on tying in the safety net. So right now, without touching the project, just having it on, I'm seeing
Now there's two things that are connected directly to the power supply right now that will be directly connected to the battery, hardwired. That's the two leads that lead from the displays into the power supply, and the two wires that connect the fan that's built into the project, that's off right now. It's not pulling any power. So the first thing we have here is the project at idle. Will be the first item that we have here at 5 volts, and we are currently sitting at 0.16. Actually, that's in amps, so it's in amps. So yeah, as long as we enter everything in the same unit, then the math will work. All right, and I'm not worried about the watts right now, because we just need the current load. Okay, so then the next thing we have here is going to be the amperage reading we're getting from the controller board. So two things are going to be connected to that: the controller itself and a second display, one of those tiny little displays that I just showed you just off to the corner of my camera. I'm not anticipating a large voltage amperage draw or a large amperage draw on that, but I'll make a note in here that I do have to put that into the math. We are going to have to include also a healthy safety net so that we don't run the battery too close to zero. Because no matter the battery technology, you don't want to push the battery all the way down to like dead, because then you damage the battery. We don't want to do that. Okay, so next thing is going to be the controller board without display. So without attaching that additional display to it, because we're going to have to account for that, but we're just not going to do it right now. I'm just going to leave a note for it. So that's on 5 volts. Now everything here is in DC power, no alternating current, all DC. So the same thing that comes out of the cigarette lighter in your car. Actually, I lied. That's 12 volts. USB cables, they're all 5. All right, so we have that, and then let me look again at what was on this dude over here. So we're sitting at point. Holy cow. 0.1. We'll say 0.13. I think that's a good value that we could play with. So we'll do 0.13. I'm gonna round that up 1/100th of an amp, because right now it's reading 0.111213. It doesn't seem to be going higher than that. So the idea here is that we want the maximum amount that it's planning on drawing. So I think that's reasonable. Okay, and then we'll then leave a note for ourselves for the controller board. Display only. Now we know that's going to be 5 volts, but we're not going to put anything in here for right now. So okay, so we need to get a reading on that, and then that's what we've got there. So now I'm going to pivot back to the camera, and then we're going to interact with some of the menus and see if the maximum, because we have to modify this right now without me touching it. We're reading about 0.13 amps of power. So we're going to manoodle through the menu and then update this if the number goes higher than that, because the idea is that we want the maximum it can draw to determine how much battery we're going to need. Okay, so now that we're back over here,
I'm gonna attempt, because everything should be long enough here that I could pick this up. I could show you what value I was looking at. So this one right here, the pink, the pink value. So it's going 0.112, 12.8, 0.9. It's not quite pushing itself into that 3 area there. Cool thing about this one though is it also gives you the wattage of your draw. So we're pulling like just over half a watt, nothing crazy. All right, now I'm going to navigate the menu here and see if I just hold in one direction. That's the other thing I was kind of curious about here, how much power. It doesn't really seem... I purposely picked one that's heavy draw for the screens, but now again, I'm going to anticipate that when we add another one of these little screens to this board so that the person who's holding the controller can see what's happening to be able to navigate the menu. I'm imagining we're going to probably slightly increase the static amperage. Maybe another, I don't know, 100, 200 milliamp, like really, really exceptionally small, like another probably 0.03 even. I don't think it's going to be that much. I'm going to need to get those values though. And that's okay, because what we can do to figure those values out is tie a multimeter into the display and see how much power that by itself is drawing. We're going to do that. We're just going to cycle back to that because I'm going to get the USB readings off of everything first. So let's see here. We got... All right, cool. Well, good to see that I have the fan hooked up right. There's stuff moving on my bench. Maximum power. I can tell you something right now for a fact. I am unbelievably excited to be able to take... I can't wait to experience what that's going to be like to wear the head to have that at maximum thrust. Jesus. Oh yeah, we're talking some mad action there from that little fan. Aha! IT Gamer. Let's try that again with the words. IT Gamer, we have a 7-stream streak watch. Thank you. That's appreciated. I really wish that there was I could tie that to a sound notification. You know, I should make an exclamation mark command for that. 110%. We have liftoff. Math means Excel. Yes, math does mean Excel, because I'm going to tell you right now, when it comes to putting in formulas, I'm not having Excel do the math for me. I'm not doing it. I have programs for that. Okay, so I did not see while navigating this menu at all these numbers change. We did not go over 0.13. So that's good news as we continue to toy around here. So I feel pretty confident that this isn't going to change much. So we're going to get our next reading. So I'm going to pull this out of there, and then we're going to pop the controller back into power by itself. So now we know how much power that draws. And now I'm going to take the microcontroller that the screens are plugged into, and we're going to start getting some answers. Now, I'm anticipating for this to pull a lot more power, because it's doing a heck of a lot more. Alright, so I'm going to see if I could scoot this over a little bit without breaking anything. I can kind of slide to the left. Because I want to be able to showcase values on here in a meaningful way. Alright, I rebooted both, so alright, cool. Alright, so let me adjust the camera so we can get a closer look up of what we're doing here. Can't wait to see the air float once you get the head put together. I know, right? You know, I don't anticipate, you know, there's the tools for reading airflow. It's CFM, and it's like really just a fan blade that you can stick in front of, you know, moving air, and it'll tell you how fast it's spinning. I have to anticipate that it's probably going to make that spin fairly quickly. I don't own one of those, but I might be tempted to go find a cheap one just to see how much air it ends up actually moving. Because where I place that fan inside of the head is really going to dictate that. The old school paper test. Yo, 100%. I already shredded at least one tissue trying to showcase how much air this little thing moves that I had that's hiding here in the corner. So yeah, there's that. That's fun. All right, let me make sure. Let me switch cameras now. And I mean do the thing. I mean zoom in with the remote. That's what I'm trying to say. All right, so I'm going to do a little more sliding to the left, and I'm going to bring us in here so that I can kind of show both of these at once. All right, cool. That's about is. There we go. That's pretty clear. You can. My goal was to get so that you could see the amperage clearly. And that actually doesn't look too bad. My captions are kind of in the way. Let me scoot up a little bit here. There we go. If any of you are looking at the captions, you can now see the reading and the captions. Much better. And I pushed it too far. Damn it. And scoot you back down a little bit. Yeah, right around there. All right, good. All right, we can see both now. Good. All right, so, all right, our at idle for the microcontroller for the screens is actually pushed over. So now we're looking at the 0.13 and like a half and 7. So we can round that up to 0.14 amp. Now, I purposely want to toggle the fan on and off and put the displays on a very heavy graphic to see how much the control voltage changes on this board. The main draw for both the displays and the tiny fan motor that's off camera right now is going to go through the variable power supply I showed you when we first started. So I want to put the system under a heavy load again and see if we jump up anymore. So we're going to leave the toothy grin and we're going to go to the BSOD. I'm going to put some blue in my face. And then I'm going to indeed set the fan back to maximum power. Hold on to your butts. I'm putting my hand in front of it this time so it doesn't blow the rest of the stuff off my bench. Alright, so we are looking at a full 2 amps on the variable power supply with only some of the LEDs on. Well, the BSOD turns technically all the blue and all the green on, but it's not truly every LED on, so that's a solid 2 amps on the variable power supply over there. And 0.1378. All right, we'll run that up to 0.14 just to be on the safe side. All right, so we got that. Switch this back over to the hard eyes so I can stop blinding myself.
Okay, so that then puts us in the face controller board is at 5 volts with a total of 0.14. We're going to round up a little bit on that because again, it's based on maximums, not average. So by rounding it up an extra 100th of an amp isn't going to hurt anything. Okay, so the next two things that we have to come into play with here is the maximum amperage of the displays and the maximum amperage of the fan. Now, I already could tell you that for our formula that we're going to put together here, that the maximum draw of the displays is 4 amps for both panels, at apparently with all of the LEDs on at once, is what Adafruit's documentation says. So when you're doing the math for it, we're just going to use a value of 4 full amps. Now, I don't believe that we're technically going to come close to that, because right now, with the basic face of the blue screen of death and the fan at maximum power, I did not pull more than 2 amps, 2 full amps. It capped out right there. So that's going to put us at, let's see here, so both LED panels, that's 5 volts at 4 amps. I said 4 amps. And then we have our high velocity cooling fan. That's at 5 volts, and that seems to be a maximum of 1 amp. Let me toggle it back on and just check the variable power supply with a basic face selected, because I don't think it's more than 1, but let me double check that. I'm not going to switch back because you guys can't see it, because I'm looking at the other display that is currently not visible, and we're worried about maximums here. So I'm just going to skip over the other options, go back to maximum power. I jumped up to 1.65. What was I at before? I should have looked at that. Alright, so at idle with both of these displays turned on, with a basic face, so I have the heart eyes up right now. I'm using 0.16 amp, and alright, let me just do a little bit of math here. We've got 0.16, and then that's going to jump up to, let's see what that jumps back up to. That's 1.6 and a half. Alright, so that puts us, I typed it backwards, so that puts this at maximum speed, subtracting the 0.16 idle amps we're getting from the displays, just to factor those out. We're pulling 1.5 amps right now at full speed. So that's at a full 5 volts, 1.5 amp at maximum speed. Now, if we were to add an additional fan, that's going to be more amperage under the system. So for right now, we're just going to try to stick with the idea of 1 of these high velocity fans. I do have an extra one. I also need the battery to run for, more than 10 minutes. So I'm going to stick with 1 for right now. Okay. Alright, so I've turned off our maximum action here. And then we're going to put in, I'm just going to round that up, that extra 100th of an amp. So we're going to say 1.5 amps. That's easy enough. So then the next one we have to get is how much power that display is going to get that's sitting on the breadboard right now. That's actually pretty easy for us to figure out. I'm going to grab out the multimeter, an additional set of test probes, and then we'll just read its amperage. So let me get that stuff out. I'll switch this back scenes and then we'll take a look at it.
Okay, so now for this one is going to be a little trickier, but I still think we can do this in a meaningful way. First thing I'm going to do is take the camera back out. Because what we're going to need to do is we're going to need to tap the amperage off of this board. So I'm going to grab out the multimeter. And then the test leads. Alright, so to get an amperage, I have to run the amperage through the meter to actually read it. So what's going to have to happen here is I need to look at the data sheet to see which of those is the positive lead. So by taking a look at our data sheet, we can see here that I have connected via this connector right here that our 3.3 volt is the red wire right there. So I have to tap onto the red wire, and then we're going to run it through the meter to then get our amperage. The nice thing about those plug-in style readers like we have right here is that you don't have to do the extra work of trying to get, you know, wedged in there. It just kind of works out. So that is our red line. So then what I'm going to do for safety's sake, I'm going to disconnect the project. And then going to unplug my red lead from there. And then to make this a little easier on myself, I've now got the two wires that when touched will complete the connection. There's a little power in the system still. I got to touch to complete this circuit to the screen. Now I'm going to touch these to the multimeter to get our amperage rating. So I'm going to set this to amperes, which is going to be down here. Now this thing is going to be an incredibly low amount of amps. So much so that the 10 amp setting is probably going to be overkill. I'm going to set this to 200 milliamp. So that'll be our setting right there. And then I'm going to position this in a way that we can both see it. So I'm going to plug this back in. And then I just have to reset the controller because unfortunately it will have forgotten its pairing. So I do have to hit the reset on the controller board. Okay, now to get our pretty picture back up, I then take both of the test leads. I do now realize you can't quite make out what's on that display. I'll just read it to you. It's a little awkward trying to get this into focus while also holding both of these at the same time. All right, so I've got the negative in this hand, and I've got the positive in this hand. And when I do that, that's going to turn the menu back on. And I'm causing it to go all kinds of wonky. What is that all about? Why are you cycling through the menu options? I'm not touching the controller. Huh. That's strange. It could be misbehaving because of the way I have this bypassed to try to get this amperage reading. That's a little strange. Let me reset both of these again. I'll reset that one. I'll have to reset on this one. Alright, so we're reading at a negative voltage because I have the leads reversed. Let me push those around. And or should I say negative amperage, rather. Oh, there's a good chance I think I pissed it off. I guess I could put that back on the in amp setting, I suppose. Because the voltage is coming from this side and then going to the screen on this side. Now this might get a little pissy because I'm trying to That's odd. This is very hard to do with two hands. I had it for a split second before and now it's not playing ball. That's odd. You know what, I wonder if it's too high of a resistance. That's 100% the problem. Alright, hold up. Alright, so the higher the resistance on the multimeter, the more oomph it's going to require to get through. Yep, that's the problem. So, this is a little hard to explain, but I wasn't getting a reading on the display over there because the higher you set the multimeter to expect more amperage, the more resistance that will be in these leads. And if the resistance is too high, not enough voltage will go to the display and we won't see anything. So I could tell you right now that I have this set to a maximum of 20 milliamps and we are reading 16. So that means that the display will move the decimal two places to the left, a maximum of 0.16 amps for the display. So, alright, cool. Let me now undo that. Again, that was a little hard to try to show and tell, but trust me on that one. That one's a little hard to try to showcase. Alright, let me undo this real quick so that we can go back to being fully functional again. Put that back over there. And plug that back in. And then we'll reset this board. And reset that board. And then we're back in action. Good. So then if I do that, go back to surprised. Alright, good. And the project still works. I'll tell you something right now. When you start moving wires around, I'll tell you something right now for a fact. That is not for the faint of heart. But, thankfully, I have some semblance of an idea of what I am doing. So, can confirm. Just have to be careful. Apparently I broke my shoulders. Can I actually be facing the camera? Bloop. There we go. Alright, so that puts us into the position of having the controller display of being 0.16. We have our reading, so I can kill that note now. So that puts us with some pretty big guns in the sense of amp draw, really just for the big LED panels. But I kind of already knew that, to expect that, for them to be that high. In practice, with the blue screen of death face on, well here, I can tell you what the reading is. The blue screen of death face is something that is the highest draw that we currently have on the project, and that pulls half an amp. So, and that's for both displays on at the same time. So that really adds a generous amount of overhead for the project as a whole. I really do believe that
it's kind of overkill, right? But to build a battery that can accommodate for this amount of load, should cover all of our bases. Because I do want to add some animations and some other silly stuff for the displays, and having LEDs are weird. It uses less power to flash an LED on and off because the LED is not on between the flashing cycles. So at the end of the day, you're using less power than as if you had all the LEDs just turned on. So in theory, an animation that has a lot of pixels going on and off, it's more process intensive on the microcontroller, but for power requirement, it's less, which feels kind of counterintuitive when you kind of think about how that more or less works out, but that's okay. That takes care of the project at idle, and then we have the controller board, we have the display. Oh, you know what? There's one more thing we don't have connected that I plan on integrating, but I don't have it wired. So I actually don't know just yet how much power it's going to need, but that's okay. We'll just do a quick Google on this. Alright, so the type of microphone that we are going to include into this, because again I do want to be able to incorporate this into the project. Because this will end up getting attached to the project as a whole, is saying that it's no more than 0.6 amp. So that kind of sounds to me a little overboard. I would think that would be more like 0.3 or 0.4, but it should be all right. All right, so then the next thing we need to do here is we need to total all of our amps here. So now what we're going to do is we're going to add a break line, and then we're going to have our total. And we're going to use the sum function because I'm not doing the math. We're using a computer. I'm going to have the computer do the math. Alright, so that's how much amperage we have. And then to figure out our wattage, I think it's just volt times watts is, yeah, amps times volts. Okay, I thought that's what it was, but it's been a hot minute. So we're going to take our voltage, multiply it by our amperage, that gets our wattage, and then we'll pull that formula down, and then we'll get our total of all of our watts. Okay, so right there is just shy of 7 full amps and about 33 and change watts of power for the project as a whole, which is fantastic to be able to kind of get that initial understanding of where we are, which is good. Okay, so now that we know that, we now then have to dictate how big of a battery we want, right? So I'm thoroughly expecting that for that amount of amp draw, that I have more than enough of a safety factor built into it, because those screens do not seem to pull anything close to 4 amps. I really feel like that's almost an extra factor of 3. Just seeing that they just don't go that high. But erring on the side of caution. We'll leave it as it is, according to the data sheet. Alright, let's see if we can figure out some battery math now. Let's see here, so... Alright, so determine our required runtime. Decide how many hours the project needs to run on a single charge. So, I'm kind of hoping that... Now, this value is going to be a little bit negotiable, but... our runtime target. And that is going to be in hours. Alright, so we have a runtime, and I would like to see if it's possible to get 12 hours of runtime. But I don't know if that's unrealistic just yet. That's going to be one of those things that we'll see. We'll see what we come up with here. Because if the battery has to be too big to do that, then if we just lower our expectations of how much runtime, then the battery becomes smaller, but more frequent battery changes, right? So if I can get away with 12 hours, that's half a day. And I truly think that that's a decent target. If it works out that I get more runtime, that's just a bonus. Alright, so let's see here. So the capacity is to take our amp hour is going to be our load current multiplied by the time. So then to figure out right, so that's going to be our battery capacity amp hour. Right, now this is the thing that you've probably seen about 1,000 times on batteries you can purchase, is its amp hour rating. And this should simply be our amperage multiplied by our target runtime. Let's see here. So calculate our capacity, amp hour or milliamp hour. Yeah, by time in hours. And then, yeah, don't plan on draining the batteries to 0. Then we have to talk about battery technology, which I don't know if I want to go with the lithium-ion batteries or like the lithium phosphate, which is a lithium battery, but it's a little heavier. Their energy density is pretty high, but being the fact that they're a little bit of a heavier battery, they're less volatile to catching on fire. Fun fact, most remote control airplane batteries, also known as RC batteries, are some of the most volatile to failure when they do. The buttons, the cylinder batteries, like the kind you'll find in a flashlight, they have a vent that lives right underneath the top of the battery, and if it fails and the energy wants to get out of the battery quickly, it vents out the top. Now granted, it vents out the top as a flamethrower of molten battery, but it doesn't blow up in your face. RC batteries and laptop batteries are sealed with no vent, so that what happens is that when those batteries fail, if they do, I'm not saying that every battery does, but if they do tend to if they fail, like the battery gets punctured between the layers, or it's one of those slow failures that the battery degrades over time, the battery will start to swell, and then the layers start to expand. And the trouble is that when one of those batteries fails on a more rapid level, they blow up. So it's very important that when you're trying to determine a safe battery capacity and type of battery for your project, that you have an idea of the safety factor that's involved with that. Which nickel metal hydride batteries, oh yeah, or nickel cadmium. I love those old remote control batteries. I had tons of toys that I say tons of toys. I had like 2 or 3 RC cars that I absolutely loved. Oh my god, loved to pieces. I still have one of them floating around here somewhere. But I had tons of batteries for that stuff, is the better phrasing, because I was constantly doing the thing, playing with them. You know, they're fun. Indeed, the cool stuff. Okay, so that is amp hour, right? Now, what we're normally used to seeing on batteries is the milliamp hour. And I'm thinking that's going to work out to an 8,000 milliamp hour battery. Let me actually do the math on that quick here, make sure I got that. So I could type that on the screen here. So we got E28. So we multiply by 1,000. Okay, so we're going to take that then and switch that over to a battery capacity in milliamp hour. I'm just going to stick it underneath it just for simplicity's sake. And that's going to be our value there times 1,000. Okay, so that then puts us with a battery to last a total of a little over 6.5 amps with 12 hours of runtime. Works out to a battery that requires slightly over 80,000 milliamps of power to keep it all running. Now, so we're talking the maximum amount of power that any of these things can have. So that would mean the displays pulling as much power as possible. That means the cooling fan in the head is just on non-stop, full speed, 12 hours. I don't anticipate having the screens on the most power consumptive activities 24/7 over the course of a 12-hour period. So realistically speaking, then we're shooting for 12 hours at the most amount of power it can pull, and then we're going to pull less than that, which means the battery should realistically last longer than the 12 hours. Exactly, yes. Building for the worst case scenario. That is actually a decent way to say that. Thank you. So assuming that I didn't miss something crucial in the math here, I probably could get close to 15 or 16 hours worth of runtime out of this with not everything on maximum capacity. Now, we do want to make sure that the battery doesn't draw too low underneath its maximum capacity. You want to anticipate that the battery doesn't go too low. So, once we determine the battery technology and the circuitry we're going to use to supply that, then we'll figure out how we could do this safely so that we can make sure that the battery doesn't draw too low to zero. Because even when your cell phone that you have in your pocket all the time, even when that hits zero, the battery itself did not hit zero. The battery hit its lowest safety voltage cutoff. And the battery itself said, that's enough, I need to protect myself, and it stopped putting out voltage to the device. Now, that's a lithium battery that has the protection circuit built into the battery. A non-protected lithium battery is the one that is assuming that the protection circuit that protects the battery is built into the device that the battery is installed into. A lot of lithium cylinder cells are sold in protected or non-protected format. The protected ones have the little bump on the top, and it looks like a AA battery. In its presentation, just much larger. That circuit on the top that makes that little bump is the protection circuit to prevent you from drawing too much power and destroying the cell or causing catastrophic failure. Nobody wants a battery fire in their pocket. Unprotected cells are flat topped and sold as a unprotected cell. There are flat top batteries that do have the protection, but you're specifically looking at the phrasing that says they're unprotected. The only place I've ever seen those in use out in the wild are for those that vape. The amount of power that comes out of a vape to activate the coils to then put the stuff into your lungs gets an immediate draw of power. And that protection of the battery happens inside of the vape itself. The trouble though is that if the circuitry is not good in the design, you're gonna lose your jaw. I don't condone it using those devices. I'm just using it as an example because that's the place I've seen them in the environment that we call, Earth. There's a decent amount of concern of when those devices fail. They tend to go off like a claymore. And again, we use batteries every day. I don't want this conversation to sound like that I'm afraid of batteries or that I want you afraid of batteries. No one should be afraid of batteries, but we need to understand that there has to be a respect for the battery. Because when you start to lose the respect for something, or you're unaware of it, that gives the ability for failure to creep in a way that you may not have anticipated. Which is why, talk to your local fire department, make sure you have smoke alarms in your home, the safety things. Because in the event that there is a worst case scenario, you are covered. Nobody wants their legs on fire. Respect the 40-volt lawnmower battery. You are very much correct. Those batteries have so much energy stored into them that if they fail in a catastrophic fashion, your eyebrows are missing. And frankly, you don't have to cut the grass anymore because your yard's gone. That's why there's all these factors to make sure that the device can be as safe as it can be. But that's also why we have to be cognitive of what we're working with. That's a pretty big to-do there. So, yeah. All right, so the next thing I want to see here now, while we're here, and we're still talking about the batteries, I am going to type on my keyboard here, because I want to see, is there such a thing in the RC world? RC batteries, like I had mentioned, are the more volatile kind. Let's see here. Let's see if that's a thing. I just look for an 80,000 milliamp hour rechargeable battery. Is that so much an actual thing? Oh, probably would help if I listed a voltage. Because I've seen power banks that are kind of chonky. But the only problem I have is that I need direct access, or that would require me to put a connector, like actual USB connector, on the wires for the screens and for the fan, so that it could be then just plugged into a power bank. Might not actually be a bad idea to use a chunky power brick, because at the end of the day, we're anticipating something that is not going to be light, but something that's still portable in a way. And also, if we do something that, hot swappability, love that. And the other thing too is that with something like that, I don't have to worry so much so about the protection side of things. Because the power bank would already have baked into it the protection circuit. So let me see here. Now this, as does most things on the internet, is a generic, but that's an 80,000 milliamp battery right there. And that's got 1, 2, 3, 4 USB type A outputs. Now, I'm less concerned about the fact that it's USB type A, because you could take any USB-C cable, plug it into an adapter, or just use a cable that is USB-C on one side and USB-A on the other. That's an easy thing to do. And I'm thinking that's pretty lucrative. That might actually be the way we go with this. Now, a couple things that do have to be considered. USB type A does not like to pull more than 2.5 amp per plug. So the power bank would have to be capable of putting out, see, that wouldn't be enough power for the displays, because if we assume that the displays are capable of going up to the full 4 amp, that would burn up the USB type A connector. So as much as I love the idea of the power bank, I don't think that's necessarily a safe thing to do. So I wonder if the USB, what, all right, let's do a little bit of typing here, because, all right, so we know that USB type A max amp. Let's figure some stuff out here. So I'm not concerned about the beefiness of the power bank. I think the 80,000 would be perfectly fine. What I'm worried about, though, is how much power that would be drawn through one physical connector, because I would need to use more than one, but we need to get some maximums here. So let's see here, USB type A max amperage. Standard USB-A ports will typically provide 0.5 amp on the low side and up to 0.9, however, dedicated charging ports, 2.4 or higher, up to 3 amp in some cases. So this is indicating that we can anticipate, yeah, what I thought, 2.5 amp. So 2.5 amp would be a bad day in America with USB type A. So let's see what USB type C's max spec is. I do not know that off the top of my head. All right, let's see here. So all right, so a couple of safety concerns here. To pull more than 3 amps through one USB Type-C cable, the cable itself has to be marked with an E mark to identify it's capable of at least 5 amps of power, so that the cable doesn't fail before the power bank would, which that makes reasonable sense. Nobody wants to be on fire, including me. Yeah, no, IT gamer, you're thinking just like I am in the USB-C space. So, okay, so if we went with the USB, all right, so this is more than just the connector now with USB-C. USB-C's got some funky stuff going on here. So if we have USB Type-C, yeah, exactly. Nobody wants their cable to go into melt mode, or wet noodle mode. We've got a couple different metrics for this. So we've got Type-C, and then what we've got here, is we have standard, comes to 3 amps max. And then we've got high power. And that is using the abbreviation of EPR. That's at 5 amps. And then if we were to go with a PD, so power delivery 3.0 spec, that's that. Why is that one listed in wattage? Why must you make me do math? Well, we already said that the wattage is the math of the voltage times the amperage. So if I were to take the 100 watt and divide that by 5, that puts out a maximum of 20 amp at 100 watts. Or if we did power delivery spec 3.1, that is 240 watts. So 240 watts at 5 volts would put us at 48 amp? That sounds ridiculous. That can't be right. Five amp up to 100 watt, 5 amp up to 240 watt. That feels really dangerous. Yeah, you are correct. The USB space very much is a mess. So much so that I'm left, I don't know, guys. That seems kind of scary. Let me double check my math on that. Like, I'm positive I did the math right, but... yeah, no, I'm not wrong. 5 volts at 100 watts is 20 amps. And then 240 was the other one. Yeah, 48 amps. 5 volts, 240 watts. Yeah, because ampere is power divided by voltage. That's horrifying. Oh boy. Alright. So, that's kind of I'm gonna file that under kind of good news and not so good news for a couple of reasons. We're just gonna border this stuff out here. Alright, so here's the next worry. I know that the code is going to be public, and something that is really easy to accidentally distinguish between which hole goes into which standard, and then putting that out to be publicly available. I know that if I document it well, there's not going to be reading involved. So I'm hesitant on doing the power bank idea for the public side of this project without maybe just building a battery. Now, granted, that makes me responsible for the idea of the charging circuits. But again, all of this is for educational content anyway. Because it's going to be a standard GNU license, which is, you know, use this at your own liability. But I also don't want to cook my own butt in the process. That's going to lead me to have to really sit down and think about how I want to handle this. But if I try to go with a power bank, the high power or an EPR port puts out a max of 5, and that would certainly cover anything that those displays could potentially want, because I'm only chaining 2 of them together. So that gives me an extra safety factor of an extra amp, and I don't think it's going to go more than an amp and a half. I really don't. The power delivery standards would be a little overkill. Their problem too is that to get access to probably any of these three, there has to be a negotiation between the device that you're plugging in and the charger. It's more than just having the port capable of going at power delivery at the spec of 3.1. There has to be a conversation between your device and that charger to indicate that it's safely capable of operating at this speed. So to pull 48 amps of power at the 3.1 PD speed, I can't just hook up a hunk of wire with no technology to indicate it's capable of accepting that. So I know that I don't know enough to be able to actually build that right now. So I would need, oh yeah, math, you better believe it. I don't think the power bank idea is going to work. I think it really is going to have to just be a hand-built battery. For safety reasons, and also for tying in, the cutoff, which will just have to be a part of the circuits that make it happen. Which is fine, because I'm less concerned about trying to actually build the charging and balancing circuit, because I want to use a pre-made BMS, battery management system, that you would then solder to your batteries, and then have that board dictate the safety of the cells so that they don't overcharge, they don't over discharge. So the safety factor is built in by someone who knows how to charge batteries in a way that, will keep your eyebrows attached to your face. So that's then going to involve figuring out how many individual cells we need, chaining them together with the BMS, and then from there, the project lives. That's going to require a little bit more work on my part to figure out, to find an appropriate BMS and to source some batteries to be able to hit the target of around, 80,000 milliamp. That's a pretty big battery. So that definitely leaves us with the feeling of, as to one would expect, a little bit more thought involved in the powering of the project, but that's okay. I knew that an off-the-shelf solution probably wouldn't be terribly practical, and knowing that the USB standard is very squish in the way that the communication has to happen, I very much plan on using the USB connectors to plug into the actual devices themselves, but that's going to involve hacking off the other end to tying it into the battery. Now, I still want it to have some kind of disconnect that allows the battery to be separated from the project. So whether that's going to be the type of disconnect that you would have on a remote control charge or remote control car battery, where there are like blades that pop into each other, or something like that to make it so that it's easy to separate the battery from the person who's using the head. I still want that to exist. I don't want the batteries to be permanently attached with no way to disconnect them, because that doesn't really bode well for transportation purposes. Not to mention that when you fly, your batteries need to stay with you, and that involves not having them permanently attached to the head. Not to say that you would ever, check a proto head and put it under the plane, because it would be in 1,000 pieces by the time you got it back. We're not planning on doing that, but just thinking about those things, because if you're going to travel with something like this, the idea is to make it so that it travels well with you. I plan on moving around with it once it's done, so putting that into the thought process is pretty important. Need fast charging, use a defibrillator, it works. Maybe once. So that definitely ties in to the thought. 12 volts HP connector. Oh god, no, not one of those. So, without putting together the math on that, I very much want the battery to be at the target voltage. So I want it to be a 5 volt battery that we put together. And here's why. When you step up voltage or you step down voltage, there is a loss of capacity when you do that. A step up converter is known as a buck converter, where you could take 5 volts and convert it to 12, but you're going to lose a factor of like 30% of your capacity in that step up, which means you need a bigger battery at a lower voltage to be able to hit the target you're aiming for. And there's also a loss of going in the other direction. I don't remember the math off the top of my head, and I don't want to make up bullshit. But just to know that when you have to take the voltage in either direction, if it doesn't match 1 for 1, there's going to be loss involved. Now, when you step a voltage down, that step down will then incur heat, because the electronics have to dissipate the extra force that the voltage is pushing, and the only place it can go is into the open environment. The energy has to dissipate in some capacity, and in those type of electronics, it's dissipated in heat. So that's a big part of that too. Yeah, exactly. Lots of loss for stepping. So the fact that right now the Protogen head is solely a 5-volt project is great, because that's 1 voltage we have to be able to put out, and then the amperage is just making sure that we can handle the amount of draw that happens all at once, and then the capacity, the amp hour, is just how long we want to keep it running for at that max, that amperage that we're running around with. So I think the target of 80,000 milliamp is going to be okay. Even if it worked out to be slightly under that, I still think the math will still be okay in coming in around the 12-hour mark, because again, not leaving everything at maximum draw all the time, I think is going to play into that. So yeah, I think that gives a little bit of direction for us. Now, working on the battery math and some other things, that is going to then pivot this project into using something that I did purchase already. I do need to get some supplies for it, but when you assemble a lithium battery pack, assuming that we do that, I think it's gonna be lithium. I kind of feel like that's the angle we're going to here. You do not use a soldering iron, because the heat from lithium cells don't like heat. And what's a soldering iron? It's heat. It's a lot of heat. And if you leave a soldering iron on a lithium battery, you can cause it to fail if it's there for too long, or you could degrade the battery. So we don't use those to join multiple lithium cells together. What we use is a welder, a battery welder, and it looks like what it sounds like. You have a couple of probes, you put them on top of the little sheet of nickel strip, you then put your foot on the pedal, and it shoots a very, very, very high amperage circuit between the 2 probes, which then spot welds the sheet of aluminum, or of nickel, directly to the top of the battery. Since the amount of amperage that goes through those 2 leads is so fast, it doesn't damage the battery, but that allows you to be able to do multiple spot welds on a lithium cell while protecting yourself and protecting the battery. I hope nothing goes wrong. Well, I can confirm for you, there will be a fire extinguisher nearby. I don't plan on needing it, but I'm going to tell you something right now. There will certainly be some testing outside of the studio to make sure that I do it right. And if something goes wrong, I won't be sitting here. So I'm going to get some practice in before we actually do it for real. Make sure what hasn't expired. I misunderstand. Oh, the extinguisher. Duh. Yeah, okay. No, that's totally valid. I was thinking about the spot welder. Derp. Yeah, right type. Oh, absolutely. So Thunder will be proud of me. I know my fire extinguisher types. You got the dry ABC chemical, which covers most of the general type of fires that you would have. Type A is for general combustibles like wood and paper. Type, let's see if I remember off the top of my head. Thunder, you correct me if I'm wrong. Type B is flammable. No, I know this. I know this because B and C are general, but general accelerant. Oh, I can't remember now. Crap. Because I know I know that B and C, there's a combination in there for consume. I can just read, but I don't have the extinguisher in front of me. All right, I'm trying to remember. I know that the K type is for flammable metals. That's the one I do know off the top of my head, and that's a specialty fire extinguisher. They're very expensive. Hang on, I'm just gonna Google it. Class B extinguishers are specifically designed to extinguish fires involving flammable liquids. Okay, cool. So then what was C? C is the electrical fire. Okay, I knew flammable liquids and electronics are different things, right? Because what's the last thing you want to do? You get a fire, right? Because the electrical socket caught on fire. If you use a water-based fire extinguisher to put out an electrical fire, you're going to have a bad time for a short time because you're not going to be conscious very long. We don't want to do that. So yeah, A is general combustibles, B is flammable liquids, Class C is electrical, Class D is flammable metals. That is such as magnesium, titanium, lithium. Yes, lithium. They have special extinguishers for that. Class K is combustible cooking. So that's kind of tied in. It's weird because grease is Class B and K, but there's also a specialty K for oils, animal fats. Anybody who has ever worked in a kitchen before, a commercial kitchen, will see that there's a pull station, usually on the wall, that will then set off the Ansel system, causing the fire extinguishers to go off. And then, you know, it's an expensive call, and the fire department shows up, and you're sad. But those are Class K a lot of the time. CO2 and dust, because foam might damage the rest of electronics, not affected. I mean, that's fair. Halogen, dude, 110%. I mean, I do actually have in one of my workspaces a CO2 extinguisher. I'll tell you something right now. That was fun to mount to the wall, because it was outside of the normal safety plan. So when the guy came in, he's like, "What's this doing here?" I'm like, "Don't you worry about it. We got it." Extinguishers for lithium batteries are only issued in battery factories and are not used by firefighters. That I did know. Nah, because I do have a couple of friends that do that kind of work, in addition to you, Thunder. And it's something that it always seemed to be that it was just a general ABC dry chemical. But I'm glad to see that you've also haven't seen them either, in that sense. But it makes sense that the D style extinguishers, which have the star icon next to them on the extinguisher, which makes them stand out, do for work. Dudes who have a hobby. All right, well, fair. You know, catching things on fire is a hobby, or putting things out that have caught on fire is a hobby. Fair enough. But the D class extinguishers have the little star around the D, to indicate that it's well, it's not paid. I thought. All right, well, I'm incorrect. I thought that was your full-time gig. I mean, to be fair, you just said that it's, you know, volunteer. That's fair. Well, we appreciate your service, because I'll tell you something right now. When somebody has an issue and their butt's on fire, to have somebody to help come put them out, I know is appreciated. They may not mention it in the moment, but I'm sure that they appreciate you showing up. Like, help a brother out, please. Word professional device in our country. That's fair. Right, no, that makes sense. I mean, I know that in my country that there's a lot more volunteer than paid departments. I don't know the statistics of it. I just know that little tidbit is a little nugget for the US-based folks. But yeah, having the right extinguisher for the right situation is super important. And there's a whole thing about that because there's also color coding and the different colors, which seems to be something that's mostly uniform in the US. But obviously, reading the extinguisher and knowing which one you have means more than any color that you'll look at. wait, what? 10% of your population are firefighters. That is hysterical. Wait, no, hold on a minute. No, Thunder. All right, this is a very important question. Okay, is there like more than one mailman? And does that mailman then proceed to deliver mail to other mailman? Or does one mailman only deliver to just residents so that no two mailmen could potentially deliver to the same person at the same time? Like the never-ending cycle of mailman delivering mail to other mailman. For those of you not picking up on the reference, I'm talking about SpongeBob. Yes, I'm stupid. I don't care. I am the dumbest smart person you'll probably know. And I certainly do fall under the classification. I can do both just fine. So which one are you feeling though? That's the question. You confused me. I was talking about the people who deliver letters, like they'll deliver paper mail that they stick it in a box, and then you come out to the box and you go do 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 do, and then you got a letter and you're looking at it and you go, haha, more bills. Why are there more bills in my mailbox? I don't want to pay more bills. Please go away. You know, that kind of activity. Yeah, so I know what a postman is, but what you said only confused me. I know you know what a postman is, but just words. Yes, I mean, to be fair, what I said was meant to be kind of confusing, so mission has been accomplished. What else can I say? But you're welcome. So yeah, protecting my butt to making sure that I, stay in the less flammable category. I certainly appreciate it. But I already know the right safety procedures for what I'm looking to do. So that's where doing the whole thing called research comes in handy. I don't necessarily know if there's going to be any safety hazard concerns on the sewing side of things, other than just making sure I don't stab myself with a sewing needle or two. But I'll probably look into that too before trying, my hand at it, just to make sure that, I don't want to meet the guy that shakes his head. The EMS guy, the EMS guy who just shakes his head and is like, don't meet me this way. Like, I don't want to be one of those stories that he has on one of his many rotating videos. Like, I don't want to be the reason for another one of those. Oh, 2 years to get your 20-year brooch. Oh, that'd be cool. Yeah, probably not YOLO on stream. Yeah, no, exactly. Again, I don't have eyebrows on camera here, but I like to keep the ones that I don't show on stream, because if I lose them, I'll probably draw them on too high, and then I'm gonna look surprised. And that's no good either. It's been a part of the department since I was 7. Yo, that's awesome. That's a long amount of commitment right there. Much excellence. Alright, I'm thinking that's probably enough ranting about batteries for right now, I think. Feeling it. So that puts us... I feel better about that. I'm glad I got to sit down with you guys to, talk that out. Because now I have a plan of what we need to figure out next. Because it's going to be certainly very important to make sure that what we put together is something not only that works, but is safe. Very much so. Whole family is firefighters, whole village too. Like, oh god. Wait, hold on. Does that mean there's is there more than 5 lawyers? Because if you got multiple families that are lawyers, that's gotta feel really weird. Oh wait, no, hold on. If you got an entire family of firefighters and like, you know, get like a small grease fire that breaks out like because you're cooking outside, who's the one running for the safety gear? Does everybody just run for it? Is someone designated to be the firefighter for the day? I have questions. 30 years old with 20 years experience the company wants. Oh yes, exactly, Pine Sap. You got the nail on the head there. Not even 30. We don't run, we groan and do what needs to be done. That's less cinematic, but you know what? That's still accurate. So you know what? That's fair. That's like having a weed whacker go out of control and it's like spinning around and jumping across the sidewalk, and then someone just calmly walks over and just hits the cutoff switch on the side, and they're like, okay, the problem's taken care of. Meanwhile, there's another person in the background running and screaming like they're absolutely on fire when they just small boo-boo. It's okay. Keep your cool. That's all you gotta do. Keep the cool. Then we cool. Sounds good? It's funny how when there's a fire and you're a firefighter, you need to call EMS, despite that, instead of just calling up the gang. Yeah, that's fair. We used to do that stuff without calling the call center. Yeah, not a lot anymore. I mean, that's fair. I mean, oh, see, but that's gonna be quite the experience all by itself, right? Because like, if you trip a fire alarm and then the gang shows up, I'm imagining they probably poke some kind of fun at you. Like, what'd you do? Burn some popcorn? like I kind of feel like that's hazing on standby. You tell me I'm wrong. I definitely feel like that's the angle. What do you mean here? It's more. It's more? Like it's worse? Of course it gets worse. Why wouldn't it get worse? Like, you probably don't hear the end of it probably for a couple months at a time. You forgot to click the chimney again, did you? Yeah, exactly. So yeah, that's... Yeah. I would expect nothing less. Like when another coworker comes to save the day. Like, okay, I just... Like, you know, can we just keep it between, you know, the two of us? Like, sure. Pans face to the camera off to the side, like in what was that old show? Like in The Office, looks off camera. Yeah, we'll keep it to ourselves. Exactly. It's one of those times. Naturally. Can the timber roof support catches fire due to heat? Oh yeah, no, that wouldn't be good. Yeah, a lot of things. Chimney fires, that's terrifying. I know nothing about that. All I know is that anytime where heat is present, you have to be careful that it's dissipated in a controlled fashion so that everybody stays safe. How not to put out a chimney fire? I mean, pour water on the fire in the furnace. Okay, I'm game. Well, hold on a minute. If the chimney itself is on fire, doesn't that mean that the terracotta has failed and then it's just exposed brick at that point? Because, all right, so, oh god, why am I such a nerd? All right, hang on, we're, all right, hold on a minute. So, hang on. All right, so we're over here now. So, right, so for those of you who don't know, chimneys are in more than one layer. There is the outer layer, which is going to be an outside border, and then that's the inner layer, and then around that is the brick layer. So this is the layer that you see on the outside of the house, the darker line. Then the terracotta is in the center. That is the flue that makes up the center of the chimney. Watch the water evaporate into a bomb. Oh, that wouldn't be good. It's not exposed inside the chimney. It's covered in soot. Ah, okay, fair. I would also anticipate that the flue probably is only capable of handling so much heat before that would cause a problem. Because if you get chimney damage, then there's, well, damage to your house. So yeah, that's less than excellent. Right, heat passes through the brick into the wood. All right, fair. That makes sense. Yeah, wood has surprisingly low heat threshold. See, back in my days when I used to do the camping thing, I used to use the magnesium flammable metal, you know, Class D fire extinguisher if you need one. The flammable magnesium burns incredibly hot. It's like something like 5,000 degrees Fahrenheit or something stupid level of hot. It transfers its heat incredibly well, which is why you can use it to ignite dry, you know, things like wood. Because that flash point is so high. That's why if you ever take a look at the camping section in like your local sporting goods store, you'll see those for sale. Because they're good for when you're trying to you know, survive in the wilderness, as the theory goes. Or, you know, you're trying to start, you know, a charcoal grill. That's really handy too. Charcoal briquettes will certainly ignite at 5,000 degrees Fahrenheit. That's for certain. I cannot. What? All right. I've seen that so many times. SMH. What is that an abbreviation for? I don't want to Google it. I don't remember.
Bob, can I get a glass of water?
Shaking my head. Thank you. I appreciate. Also, Ash, welcome on in and thank you for the hydrate. I've got coffee and water. Much excellence. So, yes. My madness aside, I think that's about all we're going to cover here for this evening. A couple other things I got to do tonight. So, next stream, let me look at my candle bits. Candle bits? Nope, calendar bits. That's the words that have escaped me at this point. That should put us, yeah, next Wednesday. That should be just fine. Protogens run on RAM. They run on Linux Lite. Oh, that's a cruel game. We'll look to be yeah, back next Wednesday around a similar starting time. So let me see who we're gonna go up into. Yes, thank you. Why are we applying? I'm just saying words, you know, in an attempt to make something fun, or at least so the theory goes. That's kind of where we're at right now. Let's see here. Ba ba da ba. All right. I know what we're doing. We're doing the thing. All right. So I put a proto sticker on my PC in hopes of protecting it from being scavenged by the brutes. The thing. Lovely.